Perfect.
All right, awesome, awesome. Okay, so like I was saying, it's a real pleasure to, be here today. In my scientific career, I have noticed a pattern, which is that most of the time when people say, I sort of grew up wanting to, be a scientist of the type that I am today or whatever, it's almost always lies. But in my case, I actually did grow up hearing about CERN like every day because my dad's an accelerator physicist. And so, it's a pleasure to be here because he always used to say, a lot of good places on Earth, but if you make it to CERN, like you've made it, right? So, without further ado, I think I would be tone deaf if, being in Geneva, I didn't begin this talk by kind of drawing attention to, a planetary topic that received the Nobel Prize a few years ago. And this is, of course, the discovery of the first extrasolar planet back in 1995 by Mayer and Coellos, just a few who were at the time working just a few miles from here. And here on the graph, what you see is the kind of famous radial velocity curve that led to the discovery of this giant extrasolar planet. And if we kind of look at how well we have done as a community in discovering extrasolar planets around other stars in the last 3 decades, the answer is we've done pretty well. There are now over 5,000 confirmed extrasolar planets, and roughly the doubling time of the census is every 27 months, right? So that's pretty good. Conversely, if you look at the solar system itself, it's more embarrassing, right? Like in the last 400 years, we have legitimately found 2 planets in the solar system, Uranus and Neptune, because everything out to Saturn, right, you can just see with your naked eye. You don't need a telescope. And since Galileo's adoption of the telescope as a scientific instrument, we've only found Uranus and Neptune. And in fact, the only planet that was actually found astronomically was Uranus. Right? The way that Uranus was discovered was Herschel, who was a royal, astronomer, would just go out and draw what he saw at night, every night, and then noticed that one particularly dim star was slowly moving across the sky, and at first thought this was a comet, but then realized it was instead a planet. And in fact, the discovery of Uranus led to perhaps the most epic story in celestial mechanics to date, which is the follow-on mathematical discovery of Neptune. Right? Immediately after Uranus was discovered, astronomers of the time began reconstructing the orbit of Uranus by going back to observations that already existed and kind of making tables of where Uranus was on the night sky and trying to do calculations to see if it was all consistent with sort of just Newtonian gravity and doing kind of perturbative calculations of the orbital dynamics. And the answer was no, it was not consistent. And this is well summarized in these tables from 1821 by Alexis Bouvard, where you can clearly tell that something is horribly wrong, right, with the orbit of Uranus, because there's a table, there's pluses and minuses, there's some cosines on the other side of the page, right? Uranus is not where it's always supposed to be. Okay? And this was quite a big problem in the sort of early 1800s. Like, why was this new planet not following the trajectory that it was supposed to be following? It was deviating sometimes kind of forward to where it was supposed to be, sometimes backwards, right? Nobody could figure it out. And so what Bouvard pointed out in this 1821 publication is that there are basically 2 explanations for the fact that Uranus is not where it's supposed to be. Explanation 1 is that the data is wrong, right? He was a good theorist, so he questioned the data first. And the second explanation is that you cannot exclude the fact that these deviations from the predicted orbit are in fact real. Okay? And Uranus is really not where it's supposed to be for a reason, because it's being perturbed externally by some other body. And it took 25 years or so for the promise of this data set to really come to fruition. But of course, as we now know, the credit to the mathematical discovery of this more distant perturber, which we now know as Neptune, goes to Urbain Le Verrier, who did this heroic perturbation theory calculation in 1846 and proved, to himself primarily, that you can explain all the data about Uranus if you just introduce an extra planet into the solar system. And what's quite remarkable about Le Verrier, aside from his handwriting, was the fact that he was largely unsuccessful in getting the observational astronomers to go and hunt for this object. He gave this talk at the Parisian Observatory in March of 1846, where he said, okay, I figured it out. If you just look over there, I promise there's a planet. And people are like, well, good talk and stuff, but no, right? We're not going to do that because as I've, by the way, discovered, observational astronomy is hard. You have to stay up all night, okay? And sometimes it doesn't work out. You want to go to sleep. But one way or another, it was an epic story because Le Verrier ended up sending a bunch of letters, and he sent one to an observatory in Berlin, and then when they got to actually looking for Neptune, they discovered it in 1 hour. They just looked where he said, found it, right? Probably went back to drinking or something. I don't know. I assume that's what they did. That's what I would do. The other interesting thing about this whole 1846 story is that the reason it worked out so well is because Le Verrier was in the right place at the right time. In 1840s, Uranus and Neptune happened to be in conjunction. So they're basically passing one another on their orbital paths. So even though the calculation of Le Verrier and his contemporary at Cambridge, Adams, actually got the orbit somewhat wrong, it was a more eccentric and longer period orbit than what Neptune really has, they got the position in the night sky exactly right. Okay, and the reason that is because you kind of didn't need to know the orbit if you're doing a close, kind of almost an impulsive calculations of two things passing one another in the solar system. So, it's pretty interesting to kind of go back and try to redo this calculation in 2011, exactly one orbital period of Neptune later, and it would not have, I think, worked out quite as beautifully. So timing is everything, as it turns out. So this was the last time, a genuine discovery of a planet was made in the solar system, 1846. There was an almost planet that was discovered in 1930 because people at the time were looking for a large object, and when Pluto was discovered, it was assumed that it was a 7 Earth mass planet, but it's not. Okay, so since then, right, the architecture of the solar system had looked and remained largely like this, right? The orbits of Jupiter, Saturn, Uranus, and Neptune, and then in blue is the orbit of Pluto. That's been the architecture of our solar system since 1930. But in parallel with the exoplanet revolution, which unfolded over the last 30 years, to which I alluded early on, there's been a parallel revolution happening in the solar system, and that has been the discovery of the Kuiper Belt. And the Kuiper Belt is nothing more than the field of these icy planetesimals, these icy debris. Each one is roughly, ranges in size from sort of the size of Geneva to the size of, LA. And they orbit beyond Neptune. So I think this is an important point to emphasize that this is not the asteroid belt, right? A lot of people are familiar with the asteroid belt that lives between Mars and Jupiter. This is a second, much more massive belt of icy bodies that lives beyond Neptune. And the process of mapping out the dynamical structure of this population of icy debris has led to the realization that the solar system's planets formed not where they are today. Okay? So if you kind of don't look at this distribution of particles in physical space, but look at it in properly chosen phase space, there's a lot of structure there. And to reproduce that structure, you need to have the solar system undergo a brief period of instability. Okay? So the kind of new rewritten early history of the solar system is that the planets form in a much more compact configuration, right? Neptune being about halfway closer to the sun than where it is today. And then over the first 10, 20 million years of the solar system's lifetime, by scattering away a primordial field of planetesimals, the solar system triggers a period of transient dynamical instability, and then the planets recircularize where they are today. This class of models, which first came onto the scene about 15, 20 years ago, are collectively known as the Nice model, because much of the work on developing the kind of details of how this instability unfolded was done in the Nice Observatory. But at this point, this is kind of both the accepted story of the solar system's early evolution, and for good reason. It matches so much of the data that we have beyond Neptune, right? So in this interpretation, all this stuff, all these debris we see beyond the orbit of Neptune are just the leftover planetesimals from this instability. Okay? And by the way, if at any point any questions arise, please don't wait till the end. Just interrupt me, right? Ask away, right? We can keep this maximally informal. Okay? So the interesting thing about the kind of proximate part of the Kuiper belt that I showed you just now, the part that lives right next to Neptune, is that if you have the solar system undergo a properly, detailed instability track, you basically explain everything, and then there are no mysteries left, except in the most distant orbits. And this is something that Mike, my partner in crime, and I noticed, inspired by the work of Trujillo and Shepard, our fellow astronomers. This is something we noticed back in 2015, is that if you look at the most distant objects that we know of in the solar system, there's two peculiar things. Right? First of all, they all kind of are tilted. They all have a common inclination and node, and it looks like they orbit in a plane that is tilted with respect to that of the solar system by about 20 degrees. And then they also all kind of point into the same direction. Okay? Now, here there's an interesting exercise that you can do. You can ask yourself immediately, okay, if you have 6 objects or 6 data points, can you really say anything statistically significant about it? And if you look at these 6 in isolation, of course you cannot. But the Kuiper belt is not made up of 6 objects, right? You can do a different kind of exercise where you say that these are 6 of the most distant objects, and what are the chances that the most distant objects will show a clustering as tight as you see, and then you arrive at a very low false alarm probability, and I'll pick up on this in a second. So the data set since 2016 has more than tripled, and now we know of something on the order of 20 of these distant KBOs, and this is what the data looks like today. If you just look at it at face value, you can sort of see, okay, there are more objects pointing into one direction than the other direction, so that pattern of clustering is definitely still there, but in fact, it's even more interesting than that. Because if you then differentiate by orbital stability, and say, I'm not only going to look at all of this stuff, I'm also going to ask each individual object, are you on your way out of the solar system because you're being scattered away by Neptune? Or in general, undergoing chaotic dynamics? Remember, the 3-body problem is chaotic. Or are you stable? And turns out this it's I think not the appropriate topic to discuss in detail on how you define the stability boundary, but if you're interested, it is a pretty cool calculation because it's a very neat application of the Cherenkov criterion to kind of this gravitational problem. Anyway, if we go back to this question, basically, at the end of the day, what matters is your perihelion distance, the distance of closest approach. How tightly does the orbit hug the orbit of Neptune? And if your perihelion distance falls below this equation that we derived earlier this year, then you're basically unstable. If it's above, then you are stable. And you can check this with numerical calculations very easily. So when you do this type of when you apply this filter to the data, what you notice immediately is that only the orbits that are stable, that are not strongly interacting with Neptune, cluster together. And that kind of immediately alerts you to the fact that this is not an observational effect. This is indeed a gravitational effect. Something is confining these objects because there is no way to bias your observations based on dynamical stability. Okay? And that's because when you do these observations, when you find Kuiper Belt objects, you don't actually know what the orbit is for 1 year. You have to find them, then you have to wait for the Earth to come around, and so that the object moves a little bit, and then you measure it again, and only then do you know the orbit. So this distinction in clustering between the dynamically stable and unstable orbits is a point that goes missed often, but it's very, very important. So if these orbits really are clustered together, right, then we can ask the question, why? In solar system dynamics, the temptation always, just like I think in cosmology, right, the temptation is to outsource all the interesting stuff to some event that happened a long, long time ago. So you can say, all right, we have this distant population, maybe it was a passing star, because after all, the solar system was born in a cluster of stars, just like most stars. So could this be some relic of a perturbation that happened 5 billion years ago? And the answer is no, it cannot. And the reason it cannot is that if you evolve these objects over billion-year timescales, they will all precess out of alignment. The differential precession timescale is about 100 million years. So this clustering could not remain stable, if you will, over the lifetime, over the 5 billion year lifetime of the solar system. Something is keeping them confined right now. So that something can in principle be anything that exerts a non-axisymmetric gravitational potential, right? It can be a 5 Earth mass hamburger, right? It can be a 5 Earth mass primordial black hole, or it could be a 5 Earth mass planet, right? Any of these things will do the job identically well. But as far as we know, the things that come most commonly in the 5 Earth mass kind of category are planetary objects. And what you're seeing now on the slides is a simulation of the solar system's full 4.5 billion year evolution, where the orbits of Uranus and Neptune are these small 2 pink circles at the center. We've introduced a perturber on this eccentric kind of roughly 10,000 year orbital period trajectory, and these gold objects are representative of the more proximate part of the Kuiper Belt where you don't see any clustering, and kind of the long period guys are these blue, or I don't know, maybe they're purple. I guess they're blue orbits there. So the way, the dynamical machinery of how a pattern of orbital clustering emerges in this story is not that, Planet 9 is sitting there and kind of, shepherding these things together. It's more that during orbital alignment, the eccentricities, the ellipticities of these Kuiper Belt objects, these test particles, go through a maximum. And because of that, the perihelion, the closest approach to the sun, gets jammed into the orbit of Neptune, and then Neptune ejects them. So Neptune, it's this interplay between Planet 9's gravity causing the orbital-aligned objects to kind of experience a peak, and then Neptune cleans them out. As a result, the surviving population of bodies are those that are anti-aligned with respect to the major axis of Planet 9's orbit. Okay? And you can do these calculations at home too, if you want. Right? These, they're relatively straightforward to do these days, and they're fun. I will draw your attention briefly to this one guy over here that's coming out of the plane of the solar system. We'll come back to something like this again in a little bit, but please just keep in the back of your mind that this kind of thing happens. Yes, sir?
Sorry, quick question.
Yeah.
Why is it that this massive object trajectory does not precess? So all the blue guys look on your picture quite chaotic, and this guy is pretty static. Why is that?
Yeah. So it actually, the reason that the orbit of Planet 9 doesn't look like it's precessing, it actually does precess by about 30 degrees over the lifetime of the solar system. But the reason is that its perihelion distance, right, is at about 250 AU. So the degree of precession, the speed of precession, is strongly controlled by the semi-minor axis of the orbit. And because these guys are all hugging the orbit of Neptune, and Planet 9 is not, Planet 9 precesses much, much slower. Okay? Precession period of 30 billion years, something greater than the age of the universe. Okay. So, I want to come back again to the question of, okay, but could this be, at the end of the day, observational, some kind of an observational effect conspiring together to create this clustering? And we looked into this very carefully last summer together with Mike, and the answer is sort of summarized in this plot, which shows as a function of the semi-major axis, right? So this is the size of the orbit, the kind of azimuthal orientation of where the orbits are pointing relative to the major axis of Planet 9. So the background kind of red coloring here is the consequence of numerical simulations. If Planet 9 is there, then things should cluster over here. And each object, okay, is also each real data point, okay, is also accompanied with a map of where it was most likely to have been observed, derived from just the full history of where things have been discovered on the night sky beyond Neptune. So the blue curve, the blue kind of color bar here, is indicating to you where things should be if it's just an observational effect. The background red is where they should be if it's a gravitational effect, and I think you don't need to be a master statistician to kind of look at this and convince yourself that objects are preferentially found at kind of the overlap of where the observational strategies allow them to be found and where Planet 9's background dynamic places them. With the exception, I think, of a couple things, like this guy is not really where it's supposed to be, this one is not. Neither is, well, this one to a lesser extent because there's observation there. But anyway, all of this put together, tells you that this line of evidence alone gives you a false alarm probability of about 0.4%, which is enough for simple people like me to gamble on. Okay, but now, yeah, quick question.
Well, so on your previous slide,
yep.
Each point corresponds to an object, right?
That's right. And so each one of these is a real object.
And you told us okay, currently how many objects have been seen, and they're all here, or it seems like you said there are around 30?
Yeah, so these are only the stable ones.
Stable ones.
Okay, so the unstable ones basically don't say anything because they're interacting so strongly with Neptune that Neptune zips their orbit around, and they're the noise, if you will. So it makes sense to do a cut on orbital stability here. Now, in the simulation, towards the end, right, when the previous slide in that movie, right, towards the end, notice that, right, how we started out, right? We started out with 10,000 orbits here. We ended up with only a handful. The reason that we don't see anything other than clustering in this simulation is because all the unstable things have been scattered out of the simulation. In reality, Neptune is actually at all times continuously replenishing the disk with just like a little bit of these unstable orbits, because it's taking things from the conventional Kuiper belt and scattering them further and further out. So there's a slow diffusive flux of unstable orbits that kind of provide a noise to the problem. So it makes sense to cut them out, because if you were to include them in the simulation, they would also not cluster. So we just throw them away. Okay? Does that make sense? All right. Thank you. Okay. Any other questions? Okay, we're good. So now I want to come back to, did you have a question? No? Okay. So now I want to come back to that orbit that I asked you to pay attention to, because when we went through our calculations, we noticed that it wasn't a fluke. Instead, there's a well-defined dynamic which takes, if Planet 9 is really there, takes these long-period objects and then tilts them on their side. Okay? And then we went and looked for these objects in the existing data set, and turns out they actually have been discovered already. Okay, nobody drew attention to them because they were discovered by a mission that was primarily looking for asteroids, so they were just like sitting there in the data set. Okay, and this is what they look like. Right, so they're very weird. They look like the wings of the solar system at which the solar system is flying back at you. Remember that the solar system formed in a disk, okay, right? And so given that the solar system formed in a disk, there is no reasonable explanation for why there should be a population of objects that are orbiting perpendicular to the plane of the solar system. It's pretty unusual. And if you check, again, for the simulations and ask where did the simulations place them, right, they're sort of in the right positions. Here, there are very complicated observational biases that make this difficult to interpret, actually. But I think it's kind of telling, right, that the model predicted the existence of a highly inclined population. That population is really there. That was quite a surprise for us. And we thought, it'd be really cool if at some point someone discovered an orbit that was kind of transitioning from being part of the main cluster to becoming one of these highly inclined objects. And my current postdoc and former student, Juliette Becker, went and did just that. Again, in archival data. Actually, in data that was also a mission that was not looking for Kuiper belt objects. This was all in the DES, like dark energy survey. Okay, turns out the story of these highly inclined bodies does not end with these long period guys. Because shortly after we, I think, published the first Planet 9 paper, there was this immediate discovery of an object, a small one, that was orbiting immediately outside of Neptune, okay, but it too was on a perpendicular orbit. And we had not seen anything like this in our calculations before. But then we realized we were doing one thing wrong, which is that every time something would make its way inside of Neptune's orbit, we would just delete those particles. And the reason we delete them is because their orbital evolution is thought to be really well understood. Once things leak inside of Neptune's orbit, then the giant planets kind of play soccer, and these particles chaotically scatter around until they reach the orbit of Jupiter. Then Jupiter scatters them in, and they become Jupiter family comets. That's how Jupiter family comets are made. So we thought, okay, these are just things that are on their way to becoming Jupiter family comets. But then we repeated the calculation with Planet 9, not deleting the particles that go inside of Neptune's orbit. And we found kind of a amazingly beautiful dynamic. Namely, again, here we have Uranus, Neptune, the orbit of Planet 9. This is a random test particle, right, a Kuiper belt object, which is doing this dance of being forced from the plane of the solar system into a orthogonal state, back and forth. But then when it hugs the orbit of Neptune, this one, rather than being scattered out, actually is instead scattered in. And eventually, it just stabilizes around the orbit of Neptune, right, in this nearly perpendicular state. Okay, so this is, the kind of solar system dynamics epitome of, if you liked it, then you should have put a ring on it, right? So we again went through and looked some more, and turns out, again, there's a whole population of these bodies. Yes, question?
Is there some conservation law that can tell you why the orbit stabilizes perpendicularly?
Yeah, so the question is there a conservation law that tells you why the orbit stabilizes perpendicularly? There is no conservation law to do this. In fact, the evolution is chaotic, so the integrals are broken. The reason it tends to stabilize in this state is because of dynamical stability. It's easier to eject things when they're in the plane of the solar system, because then encounters with the planets basically last longer, right? So your impulse is greater. When you kind of tilt things like this, right, you're piercing the solar system from above. So I think it's just that. But it is interesting, actually, to your point, that if you look at the orbital distribution of where Planet 9 puts these things, right, it's sort of non-trivial. So in this inclination versus semi-major axis space, there's a clear portion of the phase space that's missing, and this highly, this retrograde set of orbits are all tethered to the orbit of Saturn. Okay, so Saturn's at 10 AU, and here I'm plotting perihelion distance on the x-axis. So these are things with large semi-major axes that are flipped upside down that are actively scattering off of Saturn. And the way they got there is from Planet 9 induced dynamics coming in from much further away. And again, the data set here is not huge, right? These things are really, really dim, and they're hard to discover. But again, if you just kind of look at where these things are, I think the union of these two plots shows you that at least the current data set is consistent with what the model predicts. And again, there is no really other good pathway to generate these things in the appropriate proportion. Okay, in fact, I wasn't part of the study, but one of my colleagues, Nate Cabe, tried very hard to generate these objects with galactic tide and passing stars, and coming from a more distant reservoir called the Oort cloud, and just could not get them to appear in the right proportion. So again, this is completely kind of a separate line of evidence from the one we started with, because this is a different population of bodies, but it all seems to tell the same story. So if you kind of put all of these pieces together, and we did in 2019, we ran a huge kind of suite of models and asked the question of what fits best, what parameters fit best. And the answer is that the parameters that fit best is that Planet 9 is about 5 Earth masses. It seems kind of weird living in the solar system that 5 Earth masses would be preferred mass scale, but if you go and ask the galaxy what kind of extrasolar planets are the most common, right? Just the census of exoplanets that we have to date is completely dominated by sort of 4 or 5 Earth mass objects. That actually turns out to be the preferred outcome of planet formation throughout the solar system. We don't quite know why, but that is a fact. And it has a mild eccentricity, a mild inclination, and a period of about 10,000 years. And that's the match to the data. Okay, so a technology review from a rather distinct Institute of Technology said that, given the level of detail, it's easy, right, to imagine that we can just do the Leverrier thing and say, well, now we know the orbit, now we know everything, we just point over there and we find the planet, right? Like, what's the big deal? But, in fact, it is not so. And the reason it is not so is that we're in the exactly opposite dynamical regime of how Leverrier found Neptune, right? Leverrier's discovery was dominated by short periodic effects. As I mentioned already, Uranus and Neptune were in conjunction. Here, none of this stuff is in conjunction with Planet 9. In fact, we can only discover these objects at perihelion. So we only know of their orbits. We don't know, and so because we only know of their orbits, all we can calculate from their orbits is the orbit of Planet 9, not its position on its orbit. In fact, you can do this whole problem in a phase-averaged manner, and it's fun to do that, right? You just write down, you can actually kind of do it analytically, right? You write down a phase-averaged Hamiltonian for a test particle perturbed by Planet 9 and the giant planets. You can sort of get most of the physics from that exercise. And of course, because the phase-averaged calculation works, it also tells you that it doesn't contain information about the phase. So we are stuck with being able to project a large number of orbits onto the night sky when we have to search a pretty large swath of the night sky. And as I mentioned, observing is hard. Okay. I have, I think, still a little bit of time. Yeah, plenty of time. Okay, awesome. So one of the kind of exercises that Mike and I like to do is whenever we publish a paper, we try to write up like an internal, report on why we're wrong, right? Like what could possibly be wrong with what we're talking about. And we found one interesting, failure mode of all our calculations that we looked into more deeply during the pandemic. And it's kind of summarized on this beautiful picture, which is that all of our models, if you were paying attention, right, you might have noticed that all of these models assume that the sun is at the center of the universe. We draw a little box of, 0.1 or 0.2 parsecs around the sun, and everything that leaves beyond that box gets lost forever, and importantly, nothing exists beyond that box either, right? That's not really true. Okay, and for the long-term evolution of the solar system, that doesn't matter, but it matters a lot for formation. The reason it matters for formation is that the sun did not form alone. It formed in a cluster of thousands of other stars. Okay? And during the formation of the solar system, the passing stars and their perturbations would have shaped the distant population of objects that we're talking about. In fact, you know that this is a bit of a digression, but you know that the sun formed in a cluster because you can go inside of a meteorite and you can look for the consequences of aluminum-26, which has a half-life of about 700,000 years, and the solar system, in effect, was polluted with aluminum-26 very early in its lifetime, and this is why asteroids that were too small to differentiate from just the heat of formation were able to differentiate. They were heated through decay. Anyway, that's a bit of a digression, but this is one of the lines of evidence for which we know that the sun formed in a cluster. Also, most stars form in clusters, so it's not a surprise. So if the sun formed in a cluster, and it did, and if you agree that Jupiter and Saturn are also there, okay, which you should because they really exist, okay, then an unavoidable consequence of two of these things being together is the formation of something called the inner Oort cloud. Okay? So when the solar system is forming and Jupiter and Saturn are gaining mass, one of the things that they will do is as they kind of go through their runaway accretion cycle, they will scatter away all the planetesimals that are in their orbital neighborhood. And that will show no clustering. It will just kind of look like this. Okay? Now, if the solar system is alone, then they just get scattered away forever and they get lost, nothing happens. But if the solar system is in a cluster, then passing stars, and clusters are more dense solar environments, can actually come and perturb these objects at aphelion. Because of Kepler's second law, right, the orbit moves really fast when it's at perihelion and really slow when it's at aphelion. So just a gentle nudge at aphelion, a small kick, will take this orbit and kind of circularize it, detach it from the orbits of Jupiter and Saturn. So through this process, what you can do is you can take some of the material that is being scattered out as Jupiter and Saturn is forming, and then freeze it in at about 1,000 astronomical units, forming a quasi-spherical population of bodies known as the inner Oort cloud. It's confusing because the inner Oort cloud is actually unrelated to the Oort cloud. Okay, they're both called the Oort cloud, but one is very different. So the question that we asked is this. It said, we've been assuming all this time that all of the distant, population of these TNOs, these Kuiper Belt objects that kind of point towards the existence of Planet 9 have been scattered out by Neptune. But what if actually they've been scattered in by Planet 9? What if they're in fact frozen in inner Oort cloud bodies that are instead re-injected back into the solar system by Planet 9's gravity? What would happen? Do those things cluster together, right? Do they form some other population? What happens? And so what we did is we, made a model of the inner Oort cloud, simulated the evolution of the sun in its early birth environment, and this is sort of the summary of the orbital structure of the inner Oort cloud. It's not too important other than to say that it's quasi-spheroidal. And then we subjected this population to 4.5 billion years of Planet 9 and giant planet-induced evolution. What we found is that the two are indistinguishable. Qualitatively speaking, the two are indistinguishable. If these distant orbits are being scattered out by Neptune, okay, then you would get this type of pattern. If they're being scattered in by Planet 9, you would get basically the same pattern. Okay? So qualitatively, if you just go and find a distant Kuiper Belt object, you can't know if this is a Kuiper Belt object that's been scattered out, okay, or this is an inner Oort cloud object that's been scattered back in. But of course, the devil is always in the details. And the detailed structure of the detailed phase space structure of the population created from the inner Oort cloud is actually marginally different. So if this is what's happening, if the source of coming from the inner Oort cloud dominates, then our estimates for Planet 9's orbit and mass are wrong. Okay, and they're wrong in the downward direction. Okay? If the inner Oort cloud dominates as a source, then we actually need a more massive, more eccentric, and longer period Planet 9 to explain the same data. The problem is we don't know which one dominates, because we don't actually know how massive the inner Oort cloud is. We don't know how efficient these processes were 4.5 billion years ago. So this is still an open question, but it's indeed a source of uncertainty. Okay, so I'll stop with kind of a fun note, which is that my friend Eduardo Marturet, who is a conductor of the Miami Symphony, got inspired by all this and thought that Planet 9 story was really, really cool. And so he wrote this 19-minute long symphony about Planet 9 as an extension to the Planet Suite. And it was cool. I got to play with the symphony. We recorded this, I guess, in March of 21. And the other thing that we did that was fun is we kind of, when we were done, we beamed this to the International Space Station where Soichi Noguchi listened to it. We used you guys would think we used Zoom. We actually didn't. We used a more ghetto solution. We used Microsoft Teams, which is pretty much as low tech as you can go, right? But, he listened to it and said that he liked it. But one of the things that I've realized you cannot escape, in the 21st century is like once something is out, right, the reviews are in. And David Gertzman said that this performance is dripping with the usual self-importance and arrogance one can always expect from composers and musicians. But other than that, it was okay. And Smokey McPot says, bizarre science, Planet 9 meets pseudoscience, face veils. Okay, so unvaxxed, unmasked, unafraid. All right, so I think I'll kind of finish up the story here and review that there are, I think, 4 lines of evidence that point to the existence of Planet 9. They are the apsidal clustering, the fact that the population of orbits is azimuthally confined together. The second is that their orbital angular momenta are tilted in a common manner. And the other 2 have to do with the large inclination population of solar system bodies. Right. The first is that, well, they exist, which is a surprise in the first place. And the second is that this population of distant and highly inclined objects actually can get scattered back in and pollute the solar system with highly inclined centaurs. Now, as I mentioned, with connection to the inner Oort cloud, there are a couple caveats. And the caveats predominantly are that if indeed the inner Oort cloud, which is this frozen-in population of distant debris, dominates as the source of objects that creates the population that we observe, then our orbital and mass estimates need to be revised upwards, probably by about a factor of 2. Okay, a factor of 2 in astronomy generically is known as a factor of 1, so this is not maybe a huge deal, but these calculations are still need to be done. Now, of course, we haven't been just idly sitting around and not doing anything. We've been observing the sky over the last 5 years. We haven't found Planet 9, but we've been using this telescope. This is the Subaru telescope on top of Mauna Kea, and it's actually inside. I mean, I'm not going to impress anybody here by talking about a really big machine, but it's pretty fun to be inside the actual telescope because it's huge. It looks like this Mecha Godzilla thing. And one of the things, as I mentioned, that I found out is that, in theory, like when you're doing theory, bad weather is good, right? You just sit at home, just do a calculation, right? In observational astronomy, this is like the primary source of frustration, is that, things like the turbulence of the upper atmosphere will completely destroy your entire night. And in order to do these observations, they're really tricky. You have to do 3 consecutive nights, and they have to be each as good as, like the weakest link in the 3 nights completely determines the precision at which you operate. So this search is generally not an efficient search. But our colleagues in France have been doing a parallel, really interesting thing, which is they've been trying to look for Planet 9 in spacecraft data, right? Trying to see if you can match spacecraft trajectories better if you account for the existence of Planet 9. And there is a portion of the sky where the ephemerides get like 1% better. Okay, and that happens to kind of align with aphelion of where the theoretical models predict Planet 9 to be, but of course we're talking about a 1% effect, so this is not something to write home about. And still, I'm pretty excited about it, and we're starting a collaboration with JPL to look into whether or not we can do a specific mission of a few small satellites to actually precisely look for external gravitational perturbations to the solar system. Okay, so I think at this point, it's 5:25. My undergraduate advisor used to tell me that no scientific talk has ever ended too early, so I will stop here. All right, thank you.
Thank you, Konstantin, for this. Thanks, Konstantin, for this fascinating story, and we have some time for questions, so maybe I'll start from people who are present in person. So, please. Yes, please use your mic. Yes.
Yep. So imagine you have your calculation is right. I mean, let's neglect these cavities, and you know how many telescopes looking for this planet now. What will be your time estimation for finding that?
Okay, it's a good question. So I would say that it's about. So I would say that this decade will definitely know, and the real kind of contributor to that is the Vera Rubin Observatory, which is coming online, I think, in December, right? And one of the greatest things that Vera Rubin will bring to the table is that it will not be, limited by two guys, trying to press a button at, 4 in the morning at 14,000 feet, right? It just wakes up and basically does this and scans the night sky, right? And it's a very efficient survey. And because of its efficiency, my hope is that two things will happen. First of all, my hope is that it'll just find Planet 9. We'll be done with it, right? If that does not happen, at the very least, Vera Rubin should increase the count of these distant KBOs, distant objects, by an order of magnitude. And if it does, right, then we can really begin to refine our models much, much further. And I hope even start to constrain the phase on kind of a probabilistic, from a probabilistic point of view. So I think that there's an injection into this problem which is coming very soon, on maybe a time scale of a year or two. I think you have a question.
Is this an area that is suitable for machine learning techniques? I mean, it seems to me that simulations are pretty inexpensive to do, so you could train your data on that and see if you discover Planet 9 first as an orbit and then perhaps pinpoint better its location.
Yeah, so there are two ways in which machine learning is applicable. The first is of course doing the simulations themselves, and it's been useful as a predictor of orbital stability in the past, but then, as I mentioned earlier in the talk, we actually kind of figured out an analytic criterion for orbital stability, and that kind of does just as well. Where machine learning is really useful, though, is in the data analysis portion, because every image, I think, is multi-gigabyte, and we take an image every 90 seconds. So the data that you have to shift through is astounding, right? In fact, it is really staggering, right? When you're on the telescope, you can just pick a random portion of the sky and just zoom in enough, you'll find a galaxy, right? It's a amazing amount of data per 90 minutes, and to shift through all that, you just can't do it without machine learning. So we use machine learning to, do the full orbit fitting algorithms to look for, false positives, and all of this stuff is done with algorithms. And to give credit where it's due, that portion of the project, I'm not the observer, right, of the two of us. Mike Brown and Serhad are actually doing that portion of the project.
Maybe we'll take a question from Zoom. Alvaro, please go ahead.
Yeah, thank you for a very interesting talk. I'm going to ask you about something that you didn't mention, and I wonder whether it is of any interest, and that is poor old ex-planet Pluto.
Uh-huh. Yeah, but what was your question about it?
Is it of any interest in this connection? Would
yes.
you have covered it, for instance?
I see. Yeah, so the short answer is no. It's too close to Neptune to be appreciably affected by Planet 9. And one of my colleagues Matt Holman actually looked into the ephemeris of Pluto to see if he could detect something about Pluto's orbit that was not fit, kind of try to do the same calculation as Leverrier, but, in a modern way. And the short answer is no. All of the errors in Pluto's position and momentum can entirely be absorbed by our basically errors in the Kuiper belt itself that we don't have a perfect understanding of the mass distribution and all of these things. So unfortunately, Pluto does not play a role here other than, as a kind of a historical, an interesting historical footnote, because after all, Pluto was, when it was discovered, initially, thought to have been 7 Earth masses. And then they kind of could not resolve the disk of Pluto in the observations, so they decided, well, maybe it's 1 Earth mass instead. And then in 1978, when the satellite of Pluto was discovered, they kind of realized that it's 1/500th of an Earth mass. So I hope that answers your question.
Yes, it does. Thanks very much.
All right, thank you.
Please.
Yeah. Does anybody look for primordial black holes there?
Yeah, did somebody look for a primordial black hole there? So yes, there have been, this has been something that has been proposed, that this is not a planet, right? And to be clear, right, all that I can give any of you is an orbit and a mass. And as I mentioned, I don't actually care what this is. Well, obviously I care, but the simulations don't care what it's made of, right? It could be a primordial black hole. It could be, I don't know, a 5 Earth mass clump of dark matter. It could be anything. One problem with the black hole hypothesis, if you will, is that, the number density of primordial black holes that are 5 Earth masses that you would need to feasibly capture one by the sun randomly is pretty high. And that is in some tension with lensing observations, because the searches for machos from the 90s provide a pretty stringent limit on what kind of number density you can have of objects that are, Earth mass or greater floating around in free space. So yes, it can be, but I sort of doubt that it is.
So maybe I can ask you a very naive question. So as you emphasize many times, you always average, you draw these orbits, and you care only about the total mass. Could it be that instead of planet 9, you have, 5 little mini planet 9s with the total mass which follow these orbits? Is there a way that simulation can distinguish between the distribution of mass along the ring versus a point thing?
Yeah. So great question. As far as the dynamics of the Kuiper belt itself, right? If you were to take Planet 9, break it up into 5 million, tennis balls or something, right, and just send them all along the same orbit, the Kuiper belt objects could not know. However, this is all happening over 4.5 billion years, right? And as a consequence, the self-gravity of that orbit will diffuse the orbit itself. So maintaining the coherence of that perturbation is going to be a challenge over 1 billion-year timescales. That said, there are papers about this being a self-gravitational effect, like self-gravity of the Kuiper belt itself. I have a talented undergraduate student working on this problem, and I think he has demonstrated that it cannot be a self-gravitational effect. But this is a good question, because and people do think about this.
Okay, I think sorry, please.
Actually, I have a question out of curiosity, and it's not a scientific question.
Okay.
Have you been thinking, or the community has been thinking of the name that such a planet would have?
The name?
Yeah.
Yeah, David Bowie.
David Bowie.
Yeah, of course. What else could it be? There's a change.org petition addressed to, I think, me and Mike Brown and the AAS, or the IAU, right, to name this planet David Bowie. when it's discovered. And at first I thought it was a stupid idea, but now I think it's an awesome idea. Because you could have a whole, you can't just name stuff randomly, right? You've got to be thinking through, right? So like all the moons of Uranus, for example, have to be named after Shakespearean characters and so on. And like you could have a whole David Bowie mythology if Planet 9 has moons, which I hope it does, because then we can actually measure its mass. So I've come around to this. David Bowie is a good name for planet. You got Jupiter, Saturn, Uranus, Neptune, Pluto, David Bowie.
Thanks.
There is a question from the chat about Planet 9 that it will be, if we observe it, it will be a great success, but it's so far uninclined. Will it be categorized as a planet? Or, in other words, what one should do to be categorized as a planet?
Yeah. Okay. So this is a question that comes up quite a bit. Like, what determines if you're a planet or not? And there's a formal definition, which is a stupid definition, okay? Because the formal definition defines what a planet is not, right? And that's usually a bad way to define things, right? So what is a planet? A planet in the solar system, right, is a thing that gravitationally dominates its neighborhood. People like to say clears its orbit. But really what people mean by that is it's a thing that if you were to remove it, right, the architecture of the solar system would look very differently. And I think Planet 9, by that account, passes the test. If you were to remove it, the architecture of the distant solar system would not have any of this clustering or tilting of the orbits or any of this interesting stuff. So it's the most planety planet of the planets of the solar system. No other planet is more planety than Planet 9. That's what we like to say with Mike.
I don't see any other question either here or on Zoom, so let's thank Konstantin again.
All right. Thank you very much. Thank you.